Homework 18, section 8.3, confidence intervals for population proportions, video 3. This problem comes straight off a homework question. If you really want to know, it is homework 18, question 4. Yours may be a different context, and if it's the same context, it may be different values. But let's take a look at it. According to a Census Bureau report, 37% of men who worked at home are college graduates. In a survey of 500 women who worked at home, 163 were college graduates. The big question being answered here is, are these the same? Are these percentages the same for both men and women? But it's hard to compare without evidence, so let's get some evidence. Part A, calculate a point estimate for the percent of women who work at home who are college graduates. Keep in mind that a point estimate is the sample version of a population value. So we're looking for the percent of women who work at home who are all college graduates, and more specifically, a percent of a population. And so a point estimate, well, first off, percent of a population is P, so point estimate is P hat. What percent of this sample of women who worked at home were college graduates? Well, it's just 163 divided by 500. And since we're going to be doing math with that, we should probably turn it into a decimal. Let's see, if we turn that to a decimal, we should get 0.326. No, I did not divide it in my head. I used a trick. I doubled both sides of the fraction to make the denominator 1,000. I did double the top of my head, and it was 326 thousandths, which is this decimal. I'm not as smart as you think, I just know more tricks than the average person. So there's our point estimate. According to the sample, 32.6% of women who work at home are college graduates. Why is it less than the men? Well, is it necessarily? You see, the disagreement between a sample and a population, it can be boiled down to one of two things. Number one, they actually are different. But it also might be blamed on the particular sample that we took, because somebody else might have taken a sample of 500 women and gotten 40% of them. Now it's more. So anytime a sample and a population disagree, the real question is it because they're actually different, or are we just blaming it on the particular sample that we picked? I'm planting the seeds for what happens in chapter 9. But let's continue. Part B. Construct a 99.5% confidence interval. That is a large confidence level for the percent of such women. Okay, so we're going to go through the confidence interval steps. We should briefly check that the criteria are met. We're not told anything about the sample, so we're going to assume it's a simple random sample. There's 500 women in the sample. That's less than 5% of the population of all women. I'm assuming there are more than 10,000 women. Let's see. There are two criteria. You are a college graduate or you're not. And there's at least 10 in this category, and then 500 minus 163, that's 10, more than 10 in the other category. So the criteria are all met. But again, in the homework, you won't ask to be built an interval if the criteria aren't met. You might just be asked, are the criteria met? And if the answer is no, the problem is over. But let's build the interval. We've already got our point estimate, so our next move is to find the z. Remember that the z is the critical value that separates the middle area from the tails, and the area in the middle corresponds to the confidence level. Since the confidence level is 99.5%, that means that 99.5% of the area is between this negative z value and this positive z value. But in order to find the area, we need to know what the area of each tail is. Excuse me, in order to find the z's, we need to know what the area in each tail is. So if we take 100% and subtract 99.5, that means the rest is 0.5%. In other words, these two tails together equal the remaining 0.5%. But that's for both tails, so we have to divide that by 2. So one tail is half of this, which is 0.25%, or as a non-percent decimal, move the decimal 2 places to the left, and get 0.0025. So that's the area of this tail, and that's the area of this tail. And we can look up that area in the z-chart. Just remember, your z-chart tells you areas to the left of something. So when we look up the 0.0025, we're looking up this z, because that's the left area here. The left area here is 99.5% plus that. So where in the z-chart can we find 0.0025? I am looking in the negative 2.8 row. How do you know to look in the negative 2.8 row? You just skim down until you find it. Hey, there it is. And it is under the 0.01 column. And right there, perfectly, is 0.0025. So the z-score on the left is negative 2.81. And the z-score on the right is positive 2.81. Doesn't matter which one we use, we're going to do plus minus at the end. All right, so just to recap, confidence level, take it away from 100% to calculate the two tails, divide that by 2 to calculate the one tail, look up that area, tells you the negative z, change the sign to get the positive z. Oops, we're not on part C yet. We're still building the confidence interval. Here's the z. Next move is to find the standard error, which is just a formula. It's the square root of a fraction. The denominator is n. The numerator is p hat times 1 minus p hat. So, we need the square root of 0.326. And I'm not going to write 1 minus 0.326. I'm just going to calculate it. 1 minus 0.326 is 0.674. And the denominator is the sample size. There were 500 women total. So all that's going to go into the calculator, and we're going to come up with a pretty small value. I've just got a rinky-dink calculator, but it's working for now. 0.326 times 0.674, that's right, divided by 500, and we square root that. So to 4 decimal places, our standard error is 0.0210. Let me write what I see. 0.2096. But if we round that to 4 decimal places, then the 5th decimal place is bigger than 5. So we would round this number up, but it's 9. Really, what you're doing is looking at the number that's underlined, 209, and rounding it up to the next number, which would be 210. 0.0210. About to sneeze, excuse me. Allergies, not COVID, I promise. All right, so our standard error is going to be 0.0210. Then your margin of error in any confidence interval is just the product of the previous 2 results. In this case, the z-score times the standard error. So we're going to multiply 2.81 times 0.0210, and we will round that off to 4 decimal places as well. 2.81 times 0.0210, and we get to 4 decimal places 0.0590. Remember, the margin of error is what you add or subtract to the point estimate. So finally, we calculate our confidence interval. Take the point estimate, p hat, add and subtract the margin of error. So we will calculate 0.326 plus or minus the margin of error, 0.0590, and our interval in the form from one number to another. We just have to do a subtraction problem and an addition problem. 0.326 minus 0.0590 is 0.267. And if we do the addition problem, we get 0.385. And if we wrote those as percents, we could say 26.7% to 38.5%. So I'm not going to write the interpretation, but I will say it. We can state with 99.5% confidence, that's pretty confident, that the proportion of women who work at home that are college graduates is between 26.7% and 38.5%. But there's a part C. Is it reasonable to believe that the percent is the same for both men and women? Well, the Census Bureau said the percent for men was 37%. Our calculations say that we're 99.5% confident that the percent for women is between these two numbers. So is it reasonable to think that the percent of men can equal the percent of women? Well, we know that the percent of women with 99.5% confidence is between these two numbers. This number is in this interval. And because this number is in this interval, it's possible, I think the word reasonable is a little bit strong. I just used the word that was in the homework. But because this number is in this interval, it is possible that the percent of men is the same as the percent of women. So the answer to this question is yes, because 37% is in the interval. Now, if this margin of error were smaller, and this didn't quite go beyond 37%, then the answer would have been no. For example, had we done a 95% confidence interval, just kind of eyeballing this, if we had done a 95% confidence interval, this would have been 1.96, remember the last video, which means that the margin of error would have been smaller, but would have been so small that it didn't quite get this high. I don't know, I'm not going to redo the calculations. All right, so the important thing is when you're building a confidence interval for a population proportion, it's 5 steps or 4 steps depending on your perspective. Get a point estimate, a value for p hat. Get a z, that's a consequence of the confidence level. Calculate the standard error using this formula, the margin of error using this formula, and then finally the point estimate plus or minus the margin of error. And just like that, you've got your confidence interval. All right, we really only need to do one more thing. And we'll do it in the next video, but it's controlling the margin of error, because sometimes your interval is too wide and you would like to tighten up that interval. We'll take a look in the next video about what we can do to control the margin of error.